in the last class. So I just want to talk about a few of the properties of the Laplace transform now. And depending on how we go, we might get a first pass at looking at how the actual process for solving a differential equation works, okay? If we see the right properties come out. But first of all, just coming back to the table and thinking about the idea of working through all these results in the table. We've already done the first few. We've done sine and cosine. You see, a lot of them have the form of t times a function that's already on the table, okay? So you've got here on the fifth line, you've got t times the exponential, or even t to the power n times the exponential. You've got sine and cosine here, and then after them, you've got t times sine, and t times cosine. So a lot of these have the structure of t times something else that's already on the table of transforms. So this property here, theorem 2.2, theorem 2.2 deals with this general case. So it says if the Laplace transform of f of t is equal to some function f of s. Oops, sorry, can't see that. So if you've got a function that you know the transform of, then this is saying that the transform of t times the function, well, it's related to the transform of the original function f, and it's minus the derivative dds of it. Okay, so multiplying a function of t, multiplying a function by t, in terms of its transform, that's the same as taking the negative of the derivative of the transform, minus dds of f. And since those results on the table, the new function was t times the transform of something we already knew, we can work out these transforms on the right-hand side by differentiating them and so on. Now, the proof of that property is there in the notes. I don't know if I've got much more to add to it that I might put on the visualizer, other than just writing it down as I talk through it. Well, I mean, I'll just do that because that's what I like doing. But, you know, you don't necessarily have to do it. It's good practice, you know. You know, even magnificent concert pianists and stuff, they still sit down every day and do their scales, you know, they do humdrum stuff. So it's not a futile exercise just writing down known mathematics and rehearsing it in your mind. There's a strong connection between the pen and the brain, and between your hand and the brain and your mind. It helps to get things in there and helps you to understand them, I think. So the proof of this works from the right-hand side, and it works back to the left-hand side. You see, I'm thinking that I already know what the transform is. So I can write this down as the minus dds of this integral, because this is what the transform is after all, isn't it? And then I kind of do a switcheroo, that you've got a derivative on the outside and an integral. You're taking the derivative of an integral. So I reverse the orders here. And I say this is minus the integral of the derivative of the insides. Except, well, as it's written in the notes, perhaps I should write this as a partial derivative now, because the thing I'm looking at is a function of two variables. But, well, I'll just work with what I've written there. So that's interchanging the order. Interchanging the order of integration. and that derivative, dds, but now this is a derivative with respect to s, so this f factor here just passes through it, because as far as the derivative is concerned, as far as the derivative operator dds is concerned, that f of t is just acts like a fixed constant, because it has no dependence on s. So that just goes out to the front. And then we differentiate the exponential. The derivative with respect to s minus e to the st is minus t times e to the minus st. Yeah, just carrying out the differentiation of the exponential. And then you've got these two minus signs. So they're going to cancel out, give you plus. And then I just repackage it up a little bit. So the two minus signs give you plus. I'll move the exponential bit out to the front, and then I'll leave the t multiplying f of t. But you see, what are we looking at there? What are we looking at now? We're looking at an integral of an exponential e to the minus st from 0 to infinity times a certain function. Well, that's exactly the definition of a Laplace transform. The Laplace transform of something is the integral from 0 to infinity of the exponential multiplied by whatever the something is. So this is just t, f of t here. But you know, they're just exactly the lines in the notes. Kind of helps to write them down as you talk through them. So it's just using properties of the integration and differentiation to look through it. So let's see some examples of this being used. Yeah, just like in, so we already know that the Laplace transform of t is 1 over s. So the Laplace transform of t squared, after all, t squared is just t multiplied by t. So this should be minus dds of the Laplace transform of t. Minus dds of the Laplace transform of t. So that's minus dds of 1 over s squared, 1 over s. Well, the derivative of 1 over s, you all know, is minus 1 over s squared. So the extra minus sign at the front gives you 1 over s squared. Which is, hey presto, the second result, or one of the results on the table. Well, sorry, it's an instance of that one. T to the power n is n factorial over Sn plus 1. Well, could we just prove all of them in one go? What's the proof method that we could use to prove all of those in one go? Induction, yeah. You got a bunch of results indexed by the positive integers n, so you use induction. Well, we've already got the base case, because we got t, we got the transform of t. So we're going to do the Laplace transform of t to the n equals, what was it, n factorial over s to the n plus 1. So proof of all these, so we can prove this using this property of the transform we've just done. Base case is done. Well, really Laplace transform of t to the 0. And that's done. We've done that already. So we assume it's true for n equals k. Some k greater than or equal to 0, i.e. we're assuming that the Laplace transform of t to the k is k factorial over s to the power k plus 1. So the Laplace transform of t to the k plus 1, now how do I write that? How do I prepare? Well, before I go ahead and take the transform, because I want to use the assumption I've just made, I want to see the t to the k there. So you'd think of that as t times t to the k. T to the k plus 1 is t times t to the k. And now we invoke this result we've just proved, that the transform of t times some other function is minus dds of the transform of the other function. So this should be minus dds of k factorial over s to the k plus 1. Now, how do you differentiate that? We might look at it and think, oh my God, there's a k factorial in there that complicates things. Well, no, it doesn't, because k factorial doesn't have an s in it. So it's just a constant as far as differentiating with respect to s is concerned. So the k factorial moves out to the front. You got the derivative of 1 over s to the power k plus 1. And you got a minus there. Yeah. So that the derivative of 1 over s to the power k plus 1 is minus 1 over s, minus k plus 1. So leave the minus sign there. It's minus k plus 1 over s to the k plus 2. So the two minus signs cancel out. You got k plus 1 times k factorial. So that's actually k plus 1 factorial, all over s to the power k plus 2. And that is, I don't have my red pen here, but normally do these boxes in red. That is exactly the result for k plus 1. So this is the required result for n equals k plus 1. So we've done a base case. We've done the induction step, so we can assume it's true. It's true for all n. So the result from the table, that Laplace transform of t to the power n, is true for all n greater than or equal to 0. Move up. That okay? That makes sense. Any questions you'd like to ask on that? So let's do another example. There was one also, wasn't there? To take the Laplace transform of t times the cosine of omega t. Well, it's equal to what? Well, recall, we've already proved today the Laplace transform of the cosine of omega t. Was it s over s squared plus omega squared? Wasn't that it? Yeah. So applying this result, the Laplace transform of t times the cosine of omega t, this should be minus dds of s over s squared plus omega squared. Shouldn't it? Okay, because s over s squared plus omega squared is the Laplace transform of cosine of omega t. So the Laplace transform of t times cosine omega t should be minus dds of all that. Oh my God, what's that? Well, it's a little bit tricky. So that's a quotient of functions of s. So we'll need the quotient rule. Oh, crikey. Is that right? Am I thinking right? Quotient rule. Yeah. So I've got s squared plus omega squared on the bottom, so I need to square all that again. And there's a minus sign in front. And so that's my u over v, so it's v du, so it's s squared plus omega squared minus u minus s times dv, and the derivative of that is 2 times s. So seems to be s squared minus 2s squared. So that'd be minus s squared plus omega squared, but then there's a minus at the front. So it goes s squared minus omega squared. Hey? And then I've multiplied by the minus sign. See? You can't win. So hopefully that's right. S squared minus omega squared over s squared plus omega squared all squared. Okay. So yeah, so you need to keep track, especially with this where it's minus DDS. You need to keep track of all the minus signs flying around. And you know, we could do t times sine now, and you know, we could keep investigating that table merrily. These ones, well, these ones you would write the sine, or the hyperbolic sine, you would write that as a sum of exponentials, and then you just use the result about exponentials that you have above. Are you talking about these ones there? These? Sorry, which one? Yeah, so that one. So it's a good question there. What about? Yeah, so you'd write the sine part of that as it's a sum of exponentials. Well, because I wrote it down before. I wrote sine of z is a half times I times e to the minus iz minus. So you use that way of expressing sine as a sum of exponentials. And then you've got another exponentially bit, e to the minus at, that's going to multiply those. But it'll still be a sum of certain exponentials. And then you can just apply the result about exponentials from above there. Yeah. Christmas Day, as I said. I'm going to keep you going. So I think, yeah, that pretty much covers all those functions, I think. I think you could get it done on before Christmas Day. Okay, so you're just using this result about the exponentials and so on. Okay. There's another example there, example 2.5. So this is kind of an example. It's just really an exercise with notation. Can we say what the Laplace transform of any polynomial? You've got any polynomial, so I'm not saying on the summation what the starting and ending values of n are. they'll be whatever they are, but can we apply the results that we already have? Well, yeah, we can apply the linearity. So this will be the sum over n alpha I times the Laplace transform of x to the power n. And so then this is the transform n factorial over x to the n plus 1. So you can kind of, I mean, that's what it is. You could maybe bundle it up a little bit nicer. X to the minus n minus 1, something like that. Sorry, minus, don't do that. I made a bad mistake there. This is s, the new variable s. S. Don't make that mistake where you bring in that, write down the same variable. Is that correct? Okay. So I think we'll finish with this. I mean, this next property, theorem 2.3, about the transform of a derivative. This is the most important. This is a key property of the transform that's going to make the method of solving the differential equations work. Okay. If you come back and look at the ODE example we started off with, so we're going to apply the method to ODEs like this. So the thing that means that you can't just solve that equation in one go directly, the thing that's preventing you from doing that is the fact that you've got all those derivatives of different order of the unknown function y that you're trying to find. And they have to stay as separate kind of objects. There's no way you can collapse those different derivatives of different order into one. They have to stay there as separate terms. And that's, it's that inability to kind of collapse them all into one and to find out what y is that, makes the equation hard to solve. It means you can't just solve it using trivial algebraic means. So we declared that the way we're going to solve it is to take the Laplace transform of the whole equation. So there's some function g of t sitting on the right-hand side. So we can find its transform using the collection of results in the table. Because that function g of t in the examples we'll look at, that might be a polynomial function in t, or it might be a sine, some kind of sine function, or some kind of cosine function, some kind of combination of functions like that. So we can take the Laplace transform of g of t using the table. But then how are we going to take the Laplace transform? Well, we can take the Laplace transform of y. Y is unknown to us, so we'll just have to represent the transform of y as some other unknown transform. The question is the transform of dy dt, the transform of d2y dt squared. What about all of those? Will we have to represent all of those as separate unknown functions? Well, this next property about the transform tells us no, that we only need one unknown transform when we take the transform of the whole equation. Okay, so this is the property which is the transform of a derivative. So the question we want to answer, or the question that this theorem answers, is it tells you what the transform of a derivative of a function y is in terms of the transform of y. So it bears a strong connection to the transform of the function y. It more or less effectively, to all intents and purposes, it's kind of the same thing. Well, not really the same thing, but it's just a small modification, but a very manageable modification. So, well, the result is printed there in the notes, but let's kind of act like we're discovering this. So let's try and take the transform of a derivative dy dt. What is that? Well, we just use the definition. It's the integral from 0 to infinity of e to the minus st times the derivative dy dt. Okay, that's just by definition. That's just the definition of the transform. The Laplace transform of this object is the integral of the exponential times that object dt. But now, if somebody leaps out at you and shows that integral to you, what do you immediately think as a way to work it out? It's got a very special form in the way it's written down. It's hard to do because it's a product of two factors. You have to integrate, both factors depend on t, so you've got the exponential of t, and you've got derivative of a function y, which depends on t. So it's a product of two factors. Both of the factors depend on t. But one of the factors is already written as a derivative of something. So yeah, so that screams out, integrate me by parts, is what it screams out. Okay? Because this factor is already a derivative. But it's a speech bubble that's being said by the integral. Integrate me by parts. So we should do that. The rule for integrating by parts is you take the product of the original two factors, e to the minus st and the y, evaluate it at 0 and infinity, and then you subtract the integral, and you have the factor y of t, but this time you differentiate the other factor. You got e to the minus st, you differentiate that with respect to t, and you get minus s e to the minus st. Don't you? So that's integrating that by parts. Now, what about the square bracket thing? Well, evaluating it at t equals 0 is straightforward because you've got e to the 0, which is 1, times y of 0. So you get a minus y of 0. When you evaluate it at infinity, well, really you're taking the limit of it as t goes to infinity. Yeah, well, as long as we've got real part of s bigger than 0, as long as we're in that right convergence zone, assuming convergence of the exponential part, yeah, you've got e to the minus s times t. So as t gets larger and larger, assuming the real part of s is greater than 0, this exponential is going to 0. So you get 0 there. The integral part, well, you got minus minus gives you plus. But look, this s factor there, well, we're integrating with respect to t. So s is independent of t. So it can move outside the integral. But this, what are we looking at here? We're looking at integral of the exponential times y. That's exactly the Laplace transform. Integral, the exponential, times an object. That's the transform of the object. So this is minus y of 0 plus s times the Laplace transform of y. Just as it's stated there stated there in the notes. So what's crucial to observe here, so that's the end of that's the proof, or our discovery of this result. What's crucial to observe here is the way that the Laplace transform of the derivative just depends on the Laplace transform of the original function. Okay, it's multiplied by s, and you've got a constant term here, minus y of 0. But essentially, it kind of transforms into the same kind of thing. Okay? And not just for the first derivative, for any derivative now, we can iterate this result, or just keep applying this result to get the Laplace transform of any derivative, any order derivative of y. Okay. So we can say, using an induction-based proof, we can prove the corollary. But I'll just show one example of it. For instance, if I wanted the Laplace transform of the second derivative of y. Well, I don't have to now go back to the original definition of the transform, because the second derivative is just the first derivative of the first derivative. But you see, I've just worked out how to deal with these kind of things. Here I'm taking the Laplace transform of the derivative of something. Well, I just discovered how to take the Laplace transform of the derivative of something. This something here being a y. It depended on the Laplace transform of y. So now I just apply this result. Again, it's not minus y of 0 now, it's minus y, the first derivative at 0, which you can write like that. Plus s times the Laplace transform of dy dt. But that, in turn, well, you see, I just look at the previous result. I worked out that the Laplace transform of the derivative was minus y of 0 plus s times the Laplace transform of y of t. So you get this result that you get s squared times the Laplace transform of y of t minus s times y of 0, which is the initial value of 0, and then lastly minus y prime of 0. So the transform of the second derivative is very, very strongly connected to the transform of the original function y. You just have to multiply it by s squared, make a linear adjustment in s, and a constant adjustment. Okay? But it's more or less just s squared times the transform of y. Okay, and the general result for any derivative is stated there in the corollary. So the Laplace transform of the nth derivative of a function x is just the polynomial term Sn multiplied by the Laplace transform of x, then minus a polynomial in S. And the coefficients of the polynomial, the x subscript I there, well, the x subscript I, those are just the initial values of the corresponding ith derivative of x. Okay? So this result here is the n equals 2 case of the corollary. See, when you have n equals 2, this formula there involving n just reduces to this example. Except that's written in terms of y, that's written in terms of a function x. They're just the two names for the function. So, okay, any questions about that? So you need to appreciate the way the various properties of integration that you know about play their role here. So we've defined the Laplace transform as a certain integral. It's an integral transform. And the various properties we have of integration, they give us the various properties that the Laplace transform has. Okay, so I think we'll finish off. There's a small section here on inverse transforms, and we'll return to this when we come back in January. But I think just before we go, I think it is just good to have a glance at or to see an example of the method working. Now, I'll come back to this, and we'll do a lot more. We'll do a lot more work with this in January. But it's good to see an example. So the thing to have in mind is, just like I told you at the lectures last week, remember the motivating example we had, that we couldn't work out what A times B was. That was hard. So we took the logarithm of A times B. And the logarithm of A times B turned out to be the logarithm of A plus the logarithm of B. Well, that was easier to do. So we could look up these values in the table of logarithms, and we could add them together, because adding together is easy. So the logs took us that way, and the exponential function takes us back. When you take the exponential of C, you get A times B. So this, which again would be a kind of a lookup operation. Consulting a table, consulting pre-computed values. So the hard work of multiplication was turned into the easier work of addition. Well, it's that kind of thing which we can see. It's a similar thing which is going on here with the Laplace transform. So we start off, we're faced with this differential equation. So it's an order 2 differential equation, d2y dt squared minus 5 dy dt plus 4y equals 12. We've got some initial conditions. So y of 0 and y prime of 0. Y prime is the first derivative of y, remember? So both those initial conditions are 0. The first step in the process, just like the first step here was to take logarithms, the first step here is to take the Laplace transform of the whole equation. Okay, we're trying to solve the equation. So we take the Laplace transform of the whole equation. You've got a constant 12 on the right-hand side. The Laplace transform of the constant 1, remember, is 1 over s. So the transform of 12 is going to be 12 times 1 over s. So the right-hand side transforms to 12 over s. The function y, well, we don't know what the function y is. So we use the notation y bar to represent the transform of y. Okay? So y bar is the transform of y, so I've got 4 times that. But once I've decided to represent the transform of y as y bar, that means I can represent the transform of the derivative, dy dt, as sy bar minus y0, the initial value of y. And I can write the the transform of the second derivative, d2y dt squared, as s squared times y bar minus sy naught minus y1. y1 being the initial value of the first derivative. So that's the transformed equation. That's the situation that we reached at the top over here. We've taken the logarithm. But now this equation is something that needs to be solved for y bar. It features these initial conditions. After you put in those initial conditions, it reduces to this in 2.27 there. But that equation now is much easier to solve for y bar, because you've got three terms involving y bar. Well, we can bring all them together. We can factorize out the y bar. So it's the same unknown function which is mentioned in each of those three terms on the left-hand side of 2.27. Whereas in the original ODE, you've three different derivatives of y. You can't just factorize it out or treat them the same algebraically or anything. But when you're in the transformed equation, you can. So you see, on the left-hand side, you've got this polynomial multiplying y bar, s squared minus 5s plus 4. So I can simply divide both sides of that, and then I've solved the transform problem. I now know what the transform of y is. It's a certain function of s. That function there. So at that stage, you're down here at the bottom. You've worked out the logarithm of the answer you want. Yeah, question. Yeah, thank you. Yeah, it's a misprint. Yeah, minus 5s. Thank you. I think it's corrected over the page. I think it's just a slip of the finger there. So yeah, so that's a minus 5s, so that should be minus 5s. Now, see, the s has come back at the top of the next page. When you're at this stage with the logarithm, the last step is to just take the inverse transform. Take the exponential. The last stage in the process for us here with the Laplace transform will be to take the inverse Laplace transform. Now that normally involves coming back to the table of transforms and looking down the right-hand column for the function that you found and reading off its inverse transform. But now this function that we've identified here, this function of s that we've got, that 12 over s times s squared minus 5s plus 4, you won't find that anywhere in the table of Laplace transforms. We don't have anything which is something over a cubic. But there's a technique we know about, which you'll remember from last year, which is called the partial fraction expansions. So we can take this function of s and we can find its partial fraction expansion. And that gives us the function y bar as a linear combination of something over s minus 4, and something over s minus 1. So I get a linear combination of simple enough functions. Simple enough to be found on the table of Laplace transforms. Something over s is the transform of a constant. Something over s minus a constant is the transform of an exponential. So we're now ready to perform this last step here, this lookup step. Not looking up values of the exponential, but looking up values of the inverse Laplace transform from the table of Laplace transforms. So the inverse Laplace transform of 3 over s is the constant 3. Of 1 over s minus 4, it has the inverse transform e to the 4t. And minus 4 over s minus 1, it has the transform minus 4 times e to the t. And that's your function y of t. That's the solution to the original differential equation. So you have this process. You have this hard problem to solve originally, which you transform. It becomes an easier problem to solve. You solve the easier problem. Maybe a little bit of preparation needed before you can take the inverse transform, which for here was taking the partial fraction expansion. But once you've done that, just by looking up pre-computed values, you can read off the inverse transform, and you arrive back at the solution of the original problem. Okay? So we arrive back at our function y of t, which is the solution of the original ODE. Okay, so I'm glad I got to show you that kind of complete run through the process. I mean, we'll be returning to this in January. There's more to do with it. We want to be able to treat coupled ODEs, which is systems of simultaneous ODEs. And we want to enhance our picture as well by admitting more functions into it, being able to handle more complicated types of function that crop up in the ODEs we look at, okay? So we'll continue this story when I see you after Christmas. So if I don't see you before then, have a good break. Happy Christmas and so on.